The Fibonacci sequence is a fascinating number series known since ancient times. However, it was named after Leonardo Fibonacci, who described rabbit population growth with it in the 13th century. The Fibonacci sequence itself doesn't seem particularly impressive at first. Each number equals the sum of the two before it. 1 plus 1 is 2, 1 plus 2 is 3, etc. It seems to be something very simple and completely uninteresting. But the Fibonacci numbers are very special numbers with hundreds of properties, many of which are still unknown. New patterns are constantly being discovered all over the world. For example, the sum of the squares of two neighboring Fibonacci numbers is also a Fibonacci number. Additionally, every Fibonacci number is a divisor of another Fibonacci number whose position is a multiple of its own position. Thus, for example, every third Fibonacci number is divisible by 2, every fourth by 3, and so on. What really makes this slightly strange, infinite sequence interesting is that it appears in biology, astronomy, and even in music. There is a beautiful quote, "Music is felt, temporalized, audible mathematics." In this video, I'll share some examples from nature. In the next episode, we'll explore the golden ratio, including its role in astronomy. They say mathematics is the language of nature. The Fibonacci sequence is closely related to the golden ratio, which surpasses everything else in its uniqueness. The Fibonacci sequence was first referenced around 450 before Christ. Leonardo Fibonacci. However, this sequence was illustrated with the example of a rabbit breeder who wondered how many pairs of rabbits could be produced from a single pair in 1 year. To make it clear, he established that each pair, only after 1 month from birth, produces another pair every month. You start with a single pair. This pair needs a month before it can produce a new pair, so in the second month there is still only 1 pair. Now this pair is mature enough to produce a new pair. So in the third month there are 2 pairs. In the fourth month this original pair produces another pair. The pair that was born in the third month is now ready to produce a pair of its own next month. This occurs in the 5th month. The original pair and the pair that has matured each produce a new pair. And the pair that was born in the 4th month is now also mature enough to produce another pair next month. And so on. Of course, this model assumes the immortality of the rabbits, but it is only for illustration purposes. It seems as if the Fibonacci sequence is a kind of growth pattern in nature. The arrangement of the seeds in the head of a sunflower, for example, is not random at all. They are, so to speak, arranged in a mathematically precise way. If you take a closer look at the seeds, you can see spirals radiating outward. There are spirals that turn to the left and spirals that turn to the right. The number of such spirals is always a Fibonacci number. And the numbers of left-turning and right-turning spirals are always neighboring Fibonacci numbers. For example, 34 and 55, or even in larger sunflowers, 144 and 233. This is fascinating. This system is also found in, for example, daisies, pine cones, fir cones, pineapples, cabbages, the leaves on a flower stem, and so on, to be observed. For example, with the leaves on a flower stem, due to the Fibonacci arrangement, no 2 leaves are ever exactly on top of each other, which allows the leaves to get the most light this way. So it's not just the mathematical beauty of plants, but there may also be biological reasons for it, many of which we definitely don't know yet. But it goes even further. The seeds in the head are offset by exactly 137.5 degrees each. Even during the growth of the sunflower head, 137.5 degrees is the angle of the golden angle, which is based on the golden ratio. If the angle deviates by even 1 degree, it has a negative effect on the sunflower. The buttercup has 5 petals, some larkspurs have 8, the marigold has 13, some asters have 21, daisies have 34, 55, or 88. Look at the snail shell. You start with a square and add a new square in a clockwise direction each time, using the Fibonacci numbers as the side length. Now you can draw the spiral with a compass by drawing a quarter circle in each square, using the corresponding side length as the radius. That's how a snail shell is structured. This can not only be found in a snail shell, but also, for example, in the bands of hurricanes, in galaxies, and so on. The Fibonacci sequence also describes the number of ancestors of male bees. From the unfertilized egg of a queen bee, male bees, called drones, are born, and from fertilized eggs, queens or female worker bees hatch. So a drone has only one parent, while female bees have 2. This results in the following diagram for the family tree of a drone. With each preceding generation, the next Fibonacci number appears. Can these hardworking creatures, who apparently follow a mathematical system, ever give up their job as a bee? Today we know that most animals have a function on our planet. Some experts say Earth would be uninhabitable without animals. What gives animals the motivation to do this? Why does a bee produce honey? A worker bee produces just about 2 teaspoons of honey in its entire life. Is it just a coincidence these animals make something edible that's also very healthy for us? Albert Einstein said, if bees vanish, humans would only survive 4 more years. What would a world without animals be like? Animals give humans a lot of love. Sadly, the opposite is not the case. New estimates show 150 billion animals are killed worldwide each year, or 4,756 every second. In some parts of the world, animals are skinned alive or eaten while they are still alive. We have consciousness, yet we don't behave nearly as well as animals do in this world. While we have the problem of being aware of everything, the animal world has to show us how to live in harmony with this unique planet. Despite being mistreated by us for so long, animals still serve us, yet we keep driving them to extinction. Until one day, we are alone on this world and can then calmly bomb each other. Meanwhile, don't harm even the smallest insect in your room.